Hey, how's it going everyone? Welcome back to my Godot behavior tree and navigation series part 6. This should be the last video in this series. In this video, we're going to add a new wonder behavior to our enemy. So let's go ahead and jump in. First, let's take a look at how we're going to achieve our wonder behavior. So the first thing we're going to do is we're going to define a wonder behavior wonder radius R, and this R is going to represent a circle around the enemy in which we're going to pick a random point for the enemy to wander to. So to do that, first we're going to pick a random degree between 0 to 360 or 2 pi degrees. And so essentially we're going to pick a random theta degree and we're going to rotate that radius by theta degrees to here. And then we're going to pick a random number between 0 to 1 for us to multiply with our radius. So essentially, we're going to be picking a random point on this line. Let's say if we picked 0.1, so it will be here, or 0.5, then it will be in the middle, or 0.8 is going to be here. So by doing this, we pick a random degree and a random number to multiply with our radius. We can pick a random point within this circle, and we're going to use that point to set our wonder target. So basically for our enemy to move to. Now let's jump into our enemy script and let's come up here and let's define a new variable, export variable, and this should be export variable, and let's call this wonder radius, and it's going to be float, and let's give it a value of 200 for now. And the next thing we're going to do is we also need a random number generator, so let's just call this RNG, and this will be random number generator new. We can get a new random number generator by doing this, and then inside our ready function we're going to call rng.randomize. So what this does is, let's jump to the Godot documentation and take a look. So if you look up the random number generator page and look at the randomize function, it's going to tell you that it setups a time-based seed to the generator. So by doing this, you can pretty much guarantee that every time you pass in a new seed, because it's time-based, it's going to be different. So by doing this, you are getting a more random behavior than not passing in a time-based seed. So it's still pseudo-random, but it will appear to be a bit more random than before. Now we need to get a random point to move to, so let's come down here and make a new function called get random position, and this will return a vector 2. And the first thing we're going to do is we're going to get a random, so let's call this radian. Let's call it radian, and this will be, we use our random number generator to generate a random float in the range of 0 and 2 times pi, so between 0 and 360 degrees. We also need a random radius, so radius between, let's do the same, rng.random float range, so between before we said that we want it to be between 0 and 1, but you can imagine if it actually picks somewhere very close to 0, then we won't actually see the enemy move because like it's really close to its current position. So instead of picking 0, let's do something like 0.1 and 1, and then we're gonna be multiplying that with our wonder radius. And next, we're going to be getting the actual random position. Actually, let's remove this underscore. So the actual random position that we want our enemy to move to. So this will be a vector 2, and the x value will be our random radius times cosine, and pass in our degree, so random radian, and the y value will be random radius times sine degree. So this will be sine random radian. Okay, so then we're going to return that random position. So this is actually relative, so we can't just return this because this is always picking a position around the enemy within that radius circle. So we need to pass this, return this plus our get global position. So that would be our world space position. Now let's modify our code a little bit so we can reuse our move and find path function with our new wandered target. So the first thing, let's come up here and define a new variable called navigation destination. This will be a vector 2. And let's come down to our task find path. As you can see right now, we are directly using the player position. So we are always finding path to our player, but if we change this to nav destination, then we can set this destination to our player or to our wander target, and we can always just be using task find path to be pathfinding to our player or our wander target. Now you may have noticed that we changed this to our nav destination, but we are never setting it because we just defined it. Let's make some other task. Let's make a new task here called task set player target. So this task is going to set our navigation target. So nav destination, we're going to set this to our player.get global position. And let's also add a check here. We only do this if our player is not null. And then we're going to set our destination to our player and called task.succeed. But if our player is null, so we don't have a player set or we can't find one, then we will just fail the task. We also need to do the same for our wander target. So another task called task find, let's call this find random target, and this will be, let's get a new random position. Random position equals to our function get random position, and then we set our navigation destination to that random position that we retrieved. But we actually can't just be doing this, because imagine if your character is standing close to the edge of a nav mesh, then it might return a point that is outside of the nav mesh, and we want to make sure the destination we pass to our navigation system is within our nav mesh. So we're going to be calling nav2d dot get closest point, and we're going to pass in the random position. So this will return a closest point to this random position, but it's going to be guaranteed to be on our nav mesh. So that will be, we'll be able to use that in our navigation system. And then let's just call task.succeed. We can now go into our behavior tree editor and go into our enemy and open its behavior tree, and let's fix some of these. We're going to add a new selector and connect our root to the new selector and create two connections. So the first thing will go here go to our original sequence where we have line of sight to the player. Then it will find a path to the player, and then it will try to move to the player. But actually we need to do one more thing here, which is a new task that we just made. It's setting the player to our navigation target, and we need to connect it here and connect these back. And we're going to add another sequence down here, that is when we don't have a line of sight. So we can make a new task here and use task has line of sight, but we're going to be adding an inverter here. So this is going to invert the result of that node. So if the line of sight is returns fail, then this will invert it, and actually return succeed here. So by doing this, this chunk will succeed when the enemy doesn't have line of sight to the player, and this will succeed when the enemy has line of sight to the player. So by doing this, so the second task here, it's going to be task find random target. That's correct. And also task not inverter. We're going to add a new task, which is find path, and also a new task, which is move. And let's connect these. So let's talk about selector for a little bit. We know that sequence is going to run the children nodes until one of these tasks fails, and then it's going to fail out and return fail here. So what selector does is it's going to try to run its first child, and if it succeeds, then good, it won't try to run the second one. But if the first child fail, then it'll keep evaluating the following children until it finds one that succeeds, and then it will stop. So basically, sequence will try to run all of them until it sees that one fails, and then it'll return fail. But selector will try to keep running until it finds one that succeeds. So let's save this and let's give it a try. You can see that when we successfully breaks line of sight, it's gone into a wander behavior, and it just keeps on picking random points to move to, like this. And if it has line of sight to the player again, it'll try to move to the player. But the enemy behavior is kind of funny right now, because it just immediately goes into wander and just find new position to move to non-stop. It looks super busy right now, so we're gonna fix that next. So let's stop the game. What we're gonna do here is we are going to add a wait node. So let's reconnect these, connect these down here, move these down, and like that. And we're gonna add in a new wait node and connect it. So before the enemy goes into wander, it will wait for a certain amount of some count value. So we don't really know what this is right now, but we can go into our add-ons folder, behavior tree, and click on runtime, runtime.gd, and let's search for wait node. And you can see the implementation here, and you can also see that every tick, it's ticking down engine.timescale. So basically, usually the timescale is 1, but if you have your game speed up, then it'll probably be something different. But basically, it's just ticking down 1 every frame. So we can put in something like 60. So if our game is running at 60 frames per second, then this should give us 1 second of wait time. So let's give that a try. And let's break the line of sight here. And you can see that it is roughly waiting for 1 second. So that's how that wait node works. So let's stop the game here. But if you want, you can actually go in here and change the implementation yourself to be actually time-based. And you can do that by grabbing a function in the engine object, and basically you will call engine.getFramesPerSecond. So you have the frames per second in your game. You can divide 1 by frames per second, and by doing that you get the frame time. And instead of ticking down times engine.timescale every frame, you can minus actually 1 divided by engine.getFramePerSecond, and by doing that you can achieve a time-based wait node. So you can go ahead and do that if you want to, but we're just gonna keep it like this for now. But actually something weird can happen with our current setup, and I'm gonna show you that. And let's first change this count to 600, so we wait roughly around 10 seconds. And let's go into our game again, and now try to break line of sight. And now you can see that the zombie goes into its wait node, and when it's waiting, no matter what we do, even when we're standing right in front of it, it doesn't really care because it's still waiting, and it's still in that branch that is trying to do its wander behavior. So even if it gains line of sight again, it doesn't really care. It'll just keeps on doing its stuff until we stand here long enough, and then it re-evaluates the first branch, and it finds that it has line of sight to the player, and then it will start moving to the player. So we're going to try to fix that now. We're going to come back to our behavior tree, and instead of using selector, we will actually be using a priority selector. And instead of having the line of sight check in the sequence right here, we are actually going to be adding a priority condition for each of them. So add another priority condition, and let's just connect root to here and add in 2 new branches. And for our function, for our priority condition, we're going to be using line of sight right here, but we won't be able to use inverter like we were doing down here, right here. At least there's not a way that I found out. So we are going to need to pass in parameter over here so that task has line of sight function knows that whether we want it to check for line of sight or we want it to check that if it doesn't have line of sight. So we're going to need to go back to our enemy script down here to our task has line of sight function. And now let's get a parameter from our behavior tree, and let's call it inverse. This will be of type boolean, and we're going to call it task.getParam0. So this will be the first parameter in that task, and this is actually how we get our parameter from our behavior tree. So we're going to get that, and we're going to change down here to be, we're going to assign inverse to succeed. So you can see that if inverse is false, basically it will just act as normal. It will just check for line of sight. So if inverse is false, then we first set succeed to inverse, so that would be false. But then if we have found line of sight, if we have line of sight to the player, then we will set it to not inverse. So in the case of inverse being false, this succeed will be true. And if inverse is true, so we want the result to be inverse, then the succeed will be false. So by doing this, this task will succeed if it has line of sight, and we don't want it to inverse this result. And it will return fail if it doesn't have line of sight, or it has line of sight and we want the result to be inverse. Now we can go back to our behavior tree editor and pass in the parameter. So there's only number and text right here, So we're going to be using number, and we're going to be passing in 0 here, so that will be false, and 1 here to represent true. So down here, basically we want the result to be inversed, right? Because we're checking that if the enemy doesn't have line of sight, then we want it to do its wander behavior, and we can remove these 2 nodes here, and remove that, reconnect these tasks, and up here we want the line of sight result to not be inverse, so this will be false, so we pass in 0 here, and also we can remove the line of sight check from this branch. So let's quickly go over the priority selector and a priority condition here. So to put it simply, this is going to be evaluating these conditions constantly, and even if when the behavior tree is running this branch, it will constantly be evaluating the condition, and if this condition succeeds, it will just break out of the second branch and go back and execute the first branch. So by doing this, we can get rid of the issue which we saw before, that is our enemy standing still even if it gains back line of sight to the player. So let's give this new version a try. Let's try to break line of sight first. And now it's gone into its wait node, and as you can see, once it gains line of sight again, it immediately goes back to its following behavior. But there's also another issue right now. Well, to better demonstrate that issue, let's change this wait node to 1 and save your behavior tree. Let's go back again, and now let's break line of sight. You can see that it immediately goes to wander. After it loses line of sight, it will just stops following the player, even though it has a path, and it will just immediately goes into wander and find a new path to its new wander target. So you might want this behavior, you might not. This is totally a design decision here. So when the enemy loses its line of sight to the player, do you want it to keep following its current path until it reaches there, or do you want it to immediately goes into wander? So right here, we're actually gonna change that so that if it loses line of sight, it will still follow its original path until it reaches the target, and then it will go into wander. So the reason why that was happening is because we changed the original selector to this priority selector and priority condition. So right now, if the enemy is in this branch when it has line of sight, and then it lost line of sight to the player, this priority condition here will fail immediately, and then this whole branch will fail, and then it will go down to this branch. So it will immediately goes into its wander behavior. To fix that, let's just go back to our enemy script and add a very simple new task right here called function task has path. So we're just going to be checking whether we currently still have a navigation path. So if navigation path.size equals to 0, then we're gonna call task.failed. So saying that we don't have a path anymore. And we're gonna return if, oh, we have a typo here. And if our navigation path size is not 0, which means we still have a path, we're going to be calling task.succeed. Now let's go back to our behavior tree editor, and down here we actually want a new selector over here. So we will pick between this sequence. So either it goes into our wander sequence, or add another sequence up here. And if Let's use our new task if we still have path. When we lose line of sight, let's just keep on moving along that path until it reaches its destination. So until this task has path fails. So let's save this and go back to our game and test again. So you can see once the enemy loses line of sight, it will keep on following its original path until it's finished that path, and then it'll go into its wander behavior like this. So one last thing we're going to improve on for our behavior tree here is something that you probably already noticed and probably extremely bothered by it, which is that our enemy doesn't update its path once it found one to our player. So it will be following that path even if the player already left the endpoint of that path. So we're going to try to update our path constantly so it will always leads up to the player. So to do that, we are going to add a new parallel node here and add in 2 connections and connect it, and connect the second connection to our original sequence, and make a new sequence here that is setting player as target and finding a path to the player. So actually we don't need this sequence anymore. We're just gonna connect our parallel node directly to our move node. So what this is going to do is that it's gonna run these 2 branches in parallel. So it's gonna be constantly setting player to our target and then try to find a path, and then it will set the player to our target and try to find path again, and then this node will just constantly be checking if we still have a path and if we can keep moving. And as you can see, our enemy is still not updating with our new player position to get a new path to the player. So there's something wrong here, and actually let's use the behavior tree debugger to take a look at it. So let's go into our editor, click on debug, and click on the tree over here. Let's bring our game back up, and let's try to get the player up here and click on the paused over here. So you can see now that the enemy is paused, and we can see the current behavior tree state. So it has a path to the old player position. So you can see that parallel node is running, and the set player as target sequence, the task succeeded. Task find path also succeeded. So this sequence succeeded, and therefore the parallel node, it will keep running these in parallel as long as these are both running. But if it succeeded, then the parallel node won't be doing anything. Basically, it won't try to restart this branch. So that is why after it first set the player as target and found the first path leading up to that player position, it's going to stay that way. So let's close our game and our debugger. To fix that, it's actually really simple. So let's move these over here a little bit, and let's just add a new repeat node and connect it to the parallel and connect it like this. So basically this node will keep on trying to rerun the children branch for a given time. So if you put in 10 here, it will try to rerun for 10 ticks. But if we leave it at 0, then you can see that if it's 0, then it will just keep repeating until the child has failed. So in our case, we're going to be using 0 because we want it to keep running and constantly updating the player position so that it can always find the path leading up to the most updated player position. Before we test again, let's actually change this back to something higher, so probably 120 ticks. And let's also go ahead and make our enemy a little bit slower actually. So let's make it probably 100, and let's go back and give that a try. So now you can see our enemy is following the player constantly, and it's constantly finding a new path leading up to the player with its updated position. And if we can manage to break its line of sight over here, it'll go into Wonder and find a new path, move over there. But you might have noticed that every time it moves to its Wonder target destination, it's always facing to the right, so it's always resetting its rotation. And if you found that kind of weird or annoying, don't worry, we're gonna fix that right now. So let's just stop the game. Let's go into our enemy script and let's find our move along path function right here. So the reason why that was happening is that in our move along path function, it is possible that when our distance is larger than our distance to our next node, so we come into this branch, but we only have one node left in our navigation path. So what's going to happen is we're going to remove that node and we're going to try to iterate on this loop again, but the navigation path is already empty. So we're actually not going to move at all because we assign our global position only in here. So in that case, in our physics process, our velocity right here is going to be 0. And when we try to face our velocity direction, it's going to reset our rotation basically. So to fix that, let's come over here and let's make a new else if our navigation path dot size is 1. Then what we want to do is let's just copy this line, Control D and Control X, and instead we're just going to directly assign our navigation path first node position to our global position. And then let's also copy this line right here, and then we remove the node. So we're going to be moving to our destination, then remove it, so we will still have our correct velocity in that last movement. Let's go ahead and test that. And let's try to break its line of sight over here. Well, it's facing right because the end is right. But as you can see here, it is facing the correct direction and not always resetting its rotation to the right anymore. So that's it for this video and actually this whole series. This video is a little bit more packed than I expected. We did quite a lot of stuff in this one. We added a new Wonder behavior. We also changed the behavior tree a lot so that it can react to our line of sight being lost and then immediately goes into Wonder behavior, or it'll keep on moving along its original path depending on your design. So thank you so much for watching, especially if you watched the whole series. Seriously, thank you so much, and I hope you found something useful. If you did, please leave a like, comment, and subscribe. Also, don't hesitate to leave a comment to let me know if you have a series topic in mind that you would like to see. You can also buy me a coffee, link in the description, if you really enjoyed it and want to support this channel. Lastly, thanks again for watching, and I'll see you guys in the next series. Bye.